We're now going to go on and have a look at how we can use calculus, in other words, differentiation and integration in mechanics. And this is extremely useful, particularly where you have situations where the acceleration isn't constant. Everything we've looked at so far has been to do with constant acceleration. Acceleration is rarely really constant. So a couple of just points to notice first of all. Let's say you've got a graph which is x plotted against y. You know that the gradient of that curve at any point can be calculated using dy by dx. So basically dy by dx tells you the gradient of a curve if what you've got is y plotted against x. Another way of thinking of that is dy by dx actually means the rate of change of y as x varies. Okay, so it's telling you how y changes as x varies, or another way of saying that is it tells you about the rate of change of y with respect to x. So let's say we've got a graph that instead of being y against x is actually just s, which is our displacement measured against time. And if we wanted to find the gradient of our displacement time graph, well, you already know that actually the gradient of a displacement time graph is equal to the velocity. So in other words, the velocity for a displacement time graph is the gradient of the graph, and the gradient of the graph is going to be ds by dt. And what that's actually saying is that if you've got an expression for displacement and you want to find an expression for velocity, all you need to do is differentiate that expression with respect to t. So all you're actually doing, let's say we wanted to find the gradient of the graph here, we would find the gradient of the tangent, but the gradient of that tangent is going to be ds by dt. Another way of thinking of that, of course, is the fact that the velocity is the rate of change of displacement. Okay, so let's just get that. So in other words, if you've got an expression like this, let's say we know the equation of this curve is something like s equals, I don't know, 5t minus a half t squared, for example. If we wanted to find the velocity, well, the velocity would just be ds by dt. In other words, all we have to do is differentiate this. Well, that's just going to give us 5 minus 2 times a half is 1. 5 minus t, so the velocity would be 5 minus t. So for example, if we wanted to find the initial velocity, obviously it doesn't really go with the graph, but the initial velocity is going to be when t is equal to 0. So the initial velocity is going to be 5 take away 0, in other words 5 meters per second. If we wanted to find the velocity when t is equal to 10, well, when t is equal to 10, the velocity is going to be 5 take away 10. The velocity then would be minus 5 meters per second, and so on. So essentially all you need to know is that if you've got displacement, if you differentiate displacement, you get ds by dt, and that ds by dt is equal to the velocity. So differentiating displacement gives you velocity. Now, it becomes fairly obvious here that if we have to differentiate displacement to get velocity, then if we want to get from velocity back to displacement, we must do the reverse process to differentiation, which we know is called integration. So what that actually means is that if you want to go backwards from displacement to if you want to go backwards from velocity to displacement, displacement is going to be the integral of velocity with respect to time. Okay, so differentiate displacement, you get velocity. Integrate velocity, you get displacement. You're only going to have to do fairly simple examples of this. So let's say you're told that you have a particle and you know that its velocity is t squared minus 5t plus 4, and you also know that when t is equal to 0, the displacement of that particle is equal to 0. Ooh, let's just cross that out, didn't mean to do that, never mind. Okay, so let's say the question says find an expression for the displacement. So the displacement is just going to be the integral of the velocity with respect to time. In other words, the integral of t squared minus 5t plus 4 with respect to time. So let's just carry on, integrate that, integrate t squared, and you've got a third t cubed. Integrate minus 5t, and you've got minus 5 over 2t squared. integrate 4, you've got 4t. Don't forget though that when you integrate, you always have to put in a constant. So s is equal to this expression here, but that's not quite enough. We've got it in terms of t and c. I know though, because I've been told that when t is 0, s is 0. So in other words, I know that 0 is equal to, if I put t into all of that, that becomes 0, that's 0, that's 0. 0 is actually c. So my displacement is actually just 1/3 t cubed minus 5 over 2t squared plus 4t, because I've discovered that c was 0. It's not always going to be 0. And that's my expression for s in terms of t. And from that, you can find whatever you want. Okay, it's not too much of a leap now then to realize that if you have a graph which is velocity against time, and you find the gradient of that, we already know that the gradient of a velocity time graph is actually the acceleration. And to find the gradient of a velocity time graph, we know that that's going to be dv by dt. So just extending what we had from before we knew that if we have displacement and you differentiate it, then that's going to give you ds by dt, but ds by dt is actually the velocity. And if you integrate that, so go in reverse, you get back to displacement. What we've now discovered is that if you differentiate velocity, which means that you get dv by dt, and actually that is differentiating the displacement twice, so I could also write it as d2s by dt squared, that is going to give me the acceleration. And in the same way as before, if I want to get back to velocity, then I'm going to have to integrate. And really that's all there is to it. Watch out when you're doing your integration that you stick in your constant. They will give you some initial conditions. Those initial conditions will enable you to find your constant. And that's all there is to it. I'll do a later video that's got some examples.